This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so our next speaker for this session is Ramo. She will be speaking about recycling the Hessian to reduce measurement costs in adaptive variational quantum algorithms.
Hello everyone, I'm a PhD student currently at Virginia Tech, and I appreciate the opportunity to be here to talk to you about our work on recycling the Hessian to reduce the measurement cost of adaptive variational quantum algorithms. This is joint work with Professor Sophie Economou, Ed Barnes, Nick Mayhall, and Luis Paulo Santos. So we are all familiar with the variational quantum eigensolver. This is an algorithm where we use a classical computer to optimize the parameters in a quantum circuit so as to minimize the expectation value of a Hamiltonian representing a physical system of our interest with the purpose of finding its ground state. And at this point, you might be thinking, that's awkward, right? Because the main message of QTML 2024 seems to be that we should all be very, very skeptical of variational quantum algorithms. And yet here is one more talk talking about them. Well, luckily, the algorithm I will be talking to you about is Adaptive VQE, which, as Professor Ed mentioned earlier in his talk, seems to escape this curse. While in practice we verify that the algorithm does not suffer from exponentially vanishing gradients, there is no proof that it doesn't. And there is also no known subspace where the computation is restricted to that allows us to dequantize the algorithm. So the algorithm, as described by Ed in his earlier talk today, starts with a reference state that is classical, the Hartree-Fock state. And as the iterations proceed, it appends to the ansatz unitaries generated by elements in a pre-selected operator pool. The selection criterion is the magnitude of the derivative of the energy with respect to the variational parameter of each candidate operator evaluated at point 0, which we call the gradients for simplicity. So in the beginning of each iteration, we will measure all these gradients, and we will pick the operator that has the highest gradient, and we will add it to the ansatz. After adding a new operator to the ansatz, we perform a full optimization of all the parameters. The last parameter we add is initialized at 0, such that the corresponding operator will implement the identity, while all parameters carry over from one iteration to the next. And this parameter recycling strategy has benefits ranging from trainability to cost efficiency. The algorithm terminates when a certain convergence criterion is met. For example, when the total norm of the gradient vector falls below a given threshold. So this system-tailored procedure results in a reduction of the requirements to run VQE on hardware. This is the result of a classical simulation of the algorithm for beryllium hydride, a molecule represented by 14 qubits, and we use the coupled exchange operator pool that we introduced in this recent preprint. The plot shows the error in the adaptive VQE energy against the CNOT depth of the ansatz. And we have the adaptive VQE, curve in blue, and we have for reference the UCCSD point, which is the pink diamond on the corner. And we verify that adaptive VQE is able to decrease the error very fast against the CNOT depth. And in particular, it reaches chemical accuracy, which is our typical target, with a much shallower circuit than unitary coupled cluster singles and doubles. In this talk, I will focus on the optimization method in particular. So I told you that Adaptive VQE performs a full optimization of all the parameters in each iteration, such that we have a growing parameter vector from iteration to iteration. But each of these iterations is similar to just a standard VQE optimization with a fixed ansatz. One option for the optimizer is gradient descent. In this method, we just set the search direction to the opposite of the gradient vector, such that steps are taken in the direction of the biggest decrease of the cost function. This is often quite slow to convert. We have more sophisticated methods. Another option is Newton's method, where we precondition the gradient vector with the inverse of the Hessian matrix of the cost. This essentially builds a quadratic model for the wave function, for the cost function, and attempts to set the next iterate as the minimum of this quadratic model. The result is an optimization algorithm that is faster to converge at the expense of having to evaluate all the second derivatives of the cost function. Quasi-Newton methods attempt to reach a middle ground by approximating rather than evaluating the Hessian matrix. So in these methods, we attempt to reach a faster convergence rate without the overhead that comes from evaluating all these second derivatives. And quasi-Newton methods require two main ingredients. One of them is an initial approximate Hessian matrix, and another one of them is an update formula. So the standard choice for the initial approximate Hessian matrix is the identity. Why? Because this is an unbiased choice, and it doesn't require prior knowledge about the cost function. With this choice, we start by setting the search direction as opposite to the gradient, just like gradient descent does. The difference is that as the iterations proceed, we will update this matrix such that it will include information about the curvature of the cost function. And this information is updated based solely on the coefficient and gradient vectors, such that we never have to explicitly measure second derivatives. So the other ingredient is an update formula, such that we know how to update this Hessian matrix from iteration to iteration. And a popular choice is BFGS. This method works directly with the inverse of the Hessian matrix, such that we don't have to be performing matrix inversions in each iteration. And we can obtain the update formula by enforcing three conditions. First, we need to have that the quadratic model for the cost function, as obtained from a second-order Taylor expansion, must match the gradient of the actual cost function over the last two iterates. Second, the matrix must remain positive definite, such that the quadratic model always has a minimum. And finally, among all matrices satisfying these two conditions, we choose the one that minimizes the distance to the previous Hessian with respect to some norm. So when we use a BFGS optimizer for VQE, we start by feeding the optimizer a length n parameter vector, and it outputs an optimized length n parameter vector. Internally, to aid the optimization, the optimizer is transforming the n by n identity matrix into an approximation to the inverse Hessian matrix of the cost function. By the end, we usually have a fairly good approximation. Adaptive VQE does multiple optimizations, so we do this multiple times. In the first optimization, we start by feeding the optimizer length 1 parameter vector with a single zero, and it evolves this zero into an optimized coefficient for the single ansatz parameter. Internally, it's transforming the 1 by 1 identity matrix into an approximation to the inverse of the second derivative of the single element in the ansatz. In iteration I, we feed it a length I parameter vector with the I minus 1 parameters from the previous optimization with a zero appended, and it transforms this into an optimized length I parameter vector. And internally, it's transforming the I by I identity matrix into an approximate to the inverse Hessian of the Hessian matrix of the cost function. And you might be asking yourselves, isn't she just saying the same thing over and over again? And my point is exactly. We are using the same point for one optimization as we ended with in the previous optimization, and yet we constantly reinitializing the Hessian to the identity matrix. So we're discarding all the information that we acquired in the end of the previous information by doing this resetting. Our proposal is then to recycle the Hessian by noting that our second derivatives that we had at the end of the previous iteration remain exactly as valid as they were before. So in here I have the result of simulating the protocol I just described for two different systems. We have a linear chain of 6 hydrogen atoms and beryllium hydride. These are represented by respectively 12 and 14 qubits. And we have the Hessian adaptive QE with the Hessian recycling protocol in blue, while traditional adaptive QE is in red. So the plots show the number of function evaluations against the adaptive QE iteration number, or equivalently the adaptive QE optimization number. So we verify that the Hessian recycling protocol allows us to significantly decrease the number of function evaluations required in each optimization. And I don't show the error here because it's identical across the two systems. So the impact of recycling the Hessian on the energy error is negligible, even though it does allow us to significantly decrease these measurement costs. For the molecules we considered, ranging dimensions between 12 and 14 qubits, we observed a roughly 1 order of magnitude decrease in this cost. We can better understand what is happening and why we are obtaining such a big advantage by looking at one particular optimization. In this case, I consider the 75th optimization of adaptive VQE for a linear chain of 6 hydrogen atoms separated by 1 angstrom. So in the first plot on the left here, I show the error against the optimization iteration, or equivalently the line search number. And we verify that with Hessian recycling, the error is much faster to converge, so the optimization terminates after many less iterations. In the second plot, I have the distance between the search direction and Newton's direction, which is the ideal direction, so to say. So our protocol allows the search direction to much faster align with this ideal option. And finally, on the third plot, I have the distance between the last row of the exact and approximate inverse Hessians. And both algorithms start with at the same point because we have no knowledge about the second order derivatives concerning our new parameter. But by the end, our Hessian recycling protocol has reached a much lower error, even though this end happens after a lot less iterations than when we do not recycle the Hessian. And finally, we can take a look at some quantities that are relevant to evaluate the convergence of this optimization protocol. So here on the bottom plot on the left, I have the distance between the exact Hessian and the approximate Hessian along Newton's direction. And on the middle bottom plot, I have the first accepted step size in each line search. And we know that if the first quantity goes to 1, then the second one will go to 0, or the former goes to 0, then the second one will go to 1, and we will obtain superlinear convergence. And this is confirmed in the final plot on the bottom right, where we plot the ratio between the distance to solution between subsequent iterates. So if this quantity goes to 0, we know that we have attained superlinear convergence, and this is precisely what happens when we recycle the Hessian, but it does not happen when we do not recycle the Hessian. So to summarize, the structure of the Adaptive VQE protocol invites us to recycle the Hessian, and doing so results in significant savings in measurement costs. Our Hessian recycling protocol allows us to reach superlinear convergence, even under conditions where the regular protocol would not reach superlinear convergence. And this speeds up the runtime of both running the algorithm on hardware and simulating it classically. I'll be happy to take any questions.
Thank you. First question at the front. Yep.
Thank you very much. It was a really nice talk. It's really nice that you get such good approximation to the Hessian. How many samples are you using to, whenever you're measuring to estimate the Hessian, how many measurement shots are you using? Because usually you get problems like the inversion.
Yes, so we are using full classical simulation, assuming infinite number of shots. We are working on the noisy simulations, but the runtime increases a lot. And since we need to do the rotations for the measurements, and then the optimization itself takes much longer, and we need to take averages, it's very hard to perform these simulations for systems where the Hessian recycling protocol starts actually showing an advantage. So this is something that we're still working on. Thank you.
Any other question? Yes, Krista.
Thanks for the nice talk. I have one more question. So I like this protocol a lot, right? Like you update the Hessian with what you already have, so you're trying to bring everything down. But it seems like there's an implicit assumption that the Hessian somehow evolves smoothly, right? So what would you expect happens if you have a really good optimization step where you're really moving quite far into the right direction. But then I would also expect that my loss landscape changes significantly and my hashing changes significantly. And I think then it's a bit connected to the question of Marco, like, do you have a bit of an understanding of the shot overhead you would then need to to correctly update your hashing from what you've had before?
Yes, well, I don't believe that that should be a shortcoming of the Hessian recycling protocol as much as of BFGS, because when we're recycling the Hessian, we're just preserving the second derivatives between points that are exactly the same. So these steps where the Hessian would change significantly would be steps during the BFGS optimization and not necessarily the initialization of the Hessian.
Okay, I see, thank you.
Okay, we have time for one more question. If there is, there's back.
Hello. In the experiment that you showed, in the first plot, the errors in the optimization in the zero iteration are already very small. Do you know why? That both methods start already with an error at 10 to the minus 4 or something?
You mean this error?
Yeah.
Yeah, so this is just because we use the Hartree-Fock approximation as the starting state, and this is already a pretty good starting state for the molecular systems we're considering. The problem is that in quantum chemistry, you usually need to reach really low errors, and so we really do need, so this is not a viable error experimental. We need to decrease it further.
Thank you.
Okay, in the interest of time, let's thank our speaker again.